Yeah, so the previous talk can also be seen as a motivation for this project. So in the beginning, I will talk about the motivation, and then I show you the project. And this is joint work with Loïc Pujet from Stockholm. Actually, now he's in Strasbourg. Okay. So the question is, what is the syntax of type theory? And the most straightforward answer is, well, a term in type theory is just a string, right? But then there are lots of different strings. For example, this one has these spaces in it, more spaces than this one, so they should be probably identified. So then what you usually do is and then there are strings which don't really make sense, right? Like this one, because there's a 3a is not a numeral. So that's bad. We want to exclude that. So what you usually do, you define a predicate on your strings, explaining which strings are the well-formed ones. And you also define a conversion relation on strings so that you know which ones you should identify, right? This is no, that's not what you do. You go one level, you go up the abstraction level and say that terms in your program are sequences of lexical elements. And again, there are some sequences which should be identified because they only differ in the number of brackets. Then there are sequences which are not well bracketed. So again, you could define a predicate saying what is a well bracketed sequence of lexical elements, and the conversion relation explaining which strings with explicit brackets are the same. But you don't usually do that, right? So you go one level up again and say that you use abstract syntax trees, and then you know the rest of the story. So you can. But you still don't stop here, because you see there are still some, like alpha renaming, okay? So you don't want to do alpha renaming anymore, so you work with abstract binding trees instead. And I think, and then once you have abstract binding trees, finally we can stop, right? Like, as in the previous talk, my assumption is that you stopped at this level and said, okay, now I'm allowed to define a predicate saying which abstract binding trees make sense, which are the well-typed ones. And I'm also allowed to have a conversion relation, which relates these certain abstract binding trees, and then I just work with these. But in this talk, we don't stop here. We say that actually we can work with well-typed syntax, where we don't need to give a predicate saying which terms make sense, because we only list those terms which are well-typed, which make sense. We don't have non-well-typed terms, okay? And we even go, and then you see like things here on the left, they disappear, and things also get merged. And then we go even one step up and say that our well-typed syntax is quotiented by conversion. And this is a really nice kind of semantic setting. So when you say syntax in this sense, it's a quotiented syntax, so two terms which have the same output, like this number 6 and then this complicated term with x's and plus in it. These are actually equivalent. They are identified. In this abstract setting, there's no way to distinguish them. But this abstract setting also comes with a very nice notion of model. So we know what a model of our theory is. We know what the syntax is. It is just the initial model, and we can interpret the initial model in every other model. And it's an algebraic setting. We also call this like algebraic syntax. Or another way to call this is the very intrinsic syntax compared to the extrinsic syntax. Okay, so the abstract binding tree with the typing relation, where we separate correctness from the definition, that's what we call extrinsic. And if we do everything together, this is the intrinsic approach. Okay? So if you go abstract on this ladder, it forces some choices. So for example, if you are up there, the only representations you can think about is De Bruijn. You don't use variables or alpha renaming. You have it's more like combinator flavored compared to raw syntax. Also the rules, like the derivation rules or the typing rules that you see up there, they are the paranoid versions. So you know, like you can type pi type or a lambda, when you type lambda? Do you want the type A and the B to be well-typed as well in the rule, or it's enough that the term is well-typed? So these are questions. So the paranoid approach is everything is always well-typed, and we are forced to use this if we are intrinsic. Okay, and also we are forced to use explicit substitutions. But even sometimes in the extrinsic way, sometimes it's more convenient to use explicit substitutions, as we saw in the previous talk. So these are kind of forced upon us. Also, if you go up, you can't do certain things, right? If you are abstract enough already at ASTs, you cannot count the number of brackets. But some people are interested in the number of brackets, so then you need to go all the way down and work at a lower level of abstraction. Also, you cannot print the term if you are quotienting by conversion. So the best thing you can do is you have a term, you normalize it, and you print the normal form, because normalization should respect the quotient. But actually, it was an open problem for type theory until like 9 or 8 years ago, whether you can actually normalize in this very abstract setting. And the key ingredient was to define logical relations which are proof relevant. So you actually, currently we have the technology via categorical gluing to normalize type theory with proof-relevant logical relations, or this gluing, which is proof-relevant. And these are really, really beautiful short proofs of normalization or canonicity. So like canonicity for type theory, we just proved that a closed term of type Boolean is either convertible to true or false. That fits on one page, on paper. Okay, and it's very nice. It's one single model. You don't have multiple per models and gluing and relations on defined on top of each other, but it's one single model. You interpret into this model, and you get a canonical form or a normal form and the proof of correctness at the same time. You can't even do this kind of model without proof of correctness, because everything is intrinsic, so you cannot really separate the algorithm from the correctness. You can only do it at the same time. So, but the sad fact is that all the formalization of all normalization proofs and type theory work somewhere here at the abstract binding tree level, and there's no practical formalization of intrinsic syntax for type theory. Or so by intrinsic syntax here, I mean people who know CWFs. That's a notion of model of type theory, and the intrinsic syntax can be just seen as the initial CWF or the freely generated CWF. Okay, CWF is category with family, so it's some kind of categorical notion of model of type theory. And there is the gluing style normalization proof was never formalized before. So the reasons for this is that, first of all, this syntax needs quotients, and only cubical agda supports quotients, and now there's okay, so most proof assistants don't support quotients. Okay, then there's another issue, which is called transport hell. So terms are indexed by types in this intrinsic setting, because you need to make sure that you can only put together abstract syntax trees in well-typed ways. So you need to know about the type when you build the syntax tree. Okay, so here's an analogy to explain this transport issue. You can also work with vectors indexed by natural numbers, and then you define the reverse function on vectors, okay, by pattern matching. Reverse of the empty vector is empty, but when you want to define reverse of a cons, you end up something which is not well typed, because on the left-hand side, the length of this vector is 1 plus n. On the right-hand side, it's n plus 1 because of the type of plus plus. You add something at the end. Okay, so this is an issue. So you need to add a transport. Okay, and once you start adding transport, so this is transport over the commutativity of addition. And once you add transports, whenever you use this term and try to normalize it, it will get stuck at the transport, and then you need some lemma to commute the transport with different operations like function application. And this becomes really annoying and impossible to use, and that's the main reason why people don't use intrinsic syntax. Okay, and then there's another issue, which is if in extrinsic syntax you can make substitution defined by recursion, and that's very convenient because definitional equality is convenient. It's always better to have a definitional equality than a propositional equality. Okay, So the first problem is solved, I think, by cubical type theory or observational type theory. Actually, we don't yet have very usable implementations of observational type theory, but this is just a matter of time because all the theory has been developed. And this talk will solve the second and third problem at the same time to some extent. Okay? So, and this is the solution. We take a model of type theory, which can be the syntax, and we replace it by a new model which has definitional substitution laws. So all the laws about substitution are definitional, and this new model will be isomorphic. So let me illustrate which rules become definitional. For example, this is the substitution rule for pi. Right? If you substitute with anything pi, then this square bracket operation is the substitution or the instantiation operation, and then it goes under the pi, and because it's a binder, you have to decorate the second substitution with some extra stuff. Or the application rule that I showed before is definitional. Rules like this are also definitional, that if you first weaken a type, and then you substitute the last component, which the weakening needs an extra free variable with anything, is the same as not doing anything. This is also definitional. Then, like variable rules are also definitional. If you have a lambda, sorry, I messed this up. This should be v1. Sorry. Okay, this was correct, and then I made it incorrect. So if you substitute lambda of the first De Bruijn index 1, okay, then the substitution will go under the lambda and substitute v1 with t. So the result here, this should be lam of t. Sorry. Okay. I mean, you can read. The other one is also fine. If you imagine that the lam is not there, then this equation is also definitional. Okay. And then the functor laws are also definitional. So actually, this is something that you cannot make definitional in the extrinsic formulation, even if substitution is defined recursively, because this is something that you do that you can do separately from the recursive definition. But here it is definitional. Also, like rules about composition and naturality of substitution is also definitional. The only thing which is not definitional but still provable propositionally in our new isomorphic model that we get is this, that every substitution is a list of terms. This is an eta-like rule for substitution. Okay, so technically all CWF equations become definitional except this ID equation. And so an analogy to what we do here is like working with vectors. If we have a definitional semi-ring structure on natural numbers, if all the semi-ring or commutative semi-ring structure on natural numbers, so if commutativity is definitional and everything else, that every other equation that you would write about natural number is definitional, this can be, if the system could support this, then it's very convenient to work with vectors because there are no transports. And this is what we get here as well because of these substitution laws, right? Yeah, so, and the new model can replace the old one. So, for example, we can get a substitution strict syntax, and because it's isomorphic, it also has an induction principle, and we can use that induction principle to prove something. And we use this this method. So we took the intrinsic syntax, which is weak, where all the substitutions are just propositional equality, applied this method, extracted a substitution strict syntax, proved its induction principle. Because the weak syntax also had an induction principle, we could transport it to the strict syntax and then proved canonicity. And the Agda formalization of canonicity is as beautiful as the pen and paper one. So this is really nice. Okay, so let me give some analogs of what we did here. So one is difference lists in Haskell, where you want to make the ++ list concatenation definitional. Actually, you want to reassociate the list in a certain way, which is more efficient. But the result is that by replacing this functional representation makes ++ definitional. Okay. Sorry, the associativity of ++ definitional. And this is an instance of the following strictification. Any category can be turned into a category with strict category laws by replacing leaving the objects the same and replacing the morphisms by these functions between home sets. Okay? And the functions have to satisfy an equation. And because these are just functions, and function composition is associative, then the composition of morphisms will become associative. So a shorter way to say this is just the, home Ji is Yoneda J to Yoneda I natural transformation. And the Yoneda implies that the new category is isomorphic to the old one, so we can really use it as a replacement. So this is very similar to what we are doing here. Okay? On the next slide, I will show you how we are doing it, but still just some inspiration for those who know some of this stuff. So we use the main ideas come from higher order abstract syntax or logical frameworks or two-level type theory or second order generalized algebraic theories, which are all based on pre-sheaf models. Maybe another way to say this is pre-sheaf models. So what the key ingredient for the strictification is that we need a logical framework which is strict. So we need a pre-sheaf model where all the CWF stuff except this extra rule, and the pi types in CWF are also strict. Okay? By strict, I mean that all the equations are definitional. Right? So what I am doing here now, I'm really working in intentional type theory in Agda. I'm not doing extensional type theory. I'm not pen and paper. On pen and paper in extensional type theory, all the canonicity proof and normalization proof, this gluing style stuff works really nicely. Now I'm trying to transport it into Agda, and there I really need to care about these kind of definitional things. Like the pre-sheaf model hasn't been really analyzed before from a definitional behavior, except by Pierre-Marie Pedro, who defines strict pre-sheaves. He, in the paper Russian Constructivism for a Pre-Fascist Theory, and actually ordinary pre-sheaves are completely strict CWF, so all equations, including this ID equation, is also definitional in the ordinary pre-sheaf model, but I don't know how to make pi types definitional. Probably it's not possible, but if you have an idea, then let me know. So the idea of Pierre-Marie is that there is this functor from the discrete category to the same category. So the discrete category just forgets all the morphisms, okay? And then there is a precomposition functor which has a right conic extension, and analyzing this situation leads you to this definition of strict pre-sheaf, where you just say a strict pre-sheaf is just a family, so something on this side, a pre-sheaf over a discrete category, which is just the same as a family over objects, with some extra proposition which selects a sub-pre-sheaf in the image of this right conic extension. Okay, so category theorists are now happy. Another thing which is also called strictification is when models of type theory replace weak things by strict ones, where they replace isomorphisms by equalities, propositional equalities. This is not what we are doing. We are replacing propositional equality with definitional equality, okay? And there's right adjoint splitting by Hoffman and the local universes method, which do this, but this is, they also call this strictification, but it's in a different sense. So now I tell you the truth. So this is a universe closed under sigma types, okay? So I have a U and an EL, which gives the elements of the universe. The fact that U has sigma is encoded by if there's an element of U, and then a family of U over elements of A, then you get a new U, okay? And then the constructor and destructor of the sigma type is saying that an element of a sigma type is the same as an element of A and an element of B, which depends on the A. I'm sorry, this is another typo. The B should mention the A here. So this B should be B of A, okay? Right, so this is a universe closed under sigma types. Now, this is the main construction. Given a universe closed under certain type formers, for example, sigma types, you can always build a model of type theory which has exactly the same type formers, so in this case sigma types, where all the substitution laws are definitional, okay? Exactly as I described what we will do, okay? So what's the idea? This is also called contextualization, this model, this construction, because it takes a universe, which you can think about as types and terms, but they don't mention context, and give you a model which has context and substitutions and types and terms, okay? And then the context and substitutions are just the set model. They are just sets or types, meta types, right? So contexts are sets and substitutions are functions between them. And then a type in context gamma is just a family over gamma into U, which is my universe that I started with, okay? And then I can encode sigma, and then terms are also just dependent functions, which depend on the context, which is a set, and then gives you elements of the universe, okay? So this like combines the those who know the standard or metacircular model or set model of type theory, this is that combined with the universe, okay? Types and terms are a universe. And then, magically, if you look in this model, the substitution law of sigma is just definitional. These equations hold by definition because substitution is just function composition. Function composition is definitionally associative, and it definitionally commutes with everything. Okay? So this is the main idea here. Okay? So this is a substitution strict model. It's called contextualization, or I mentioned what this is. And now what we need to do, okay, so this is one component. Maybe this is the original component. And then what we all know is that internally to Pujet's over a given model of type theory, there's a universe available which is closed under exactly the same type formers as the model of type theory that I started with. Okay? Okay? So what I need to do is just I do this replacement, taking the universe and creating a substitution strict out of it internally to a Pujet model. And the problem is I'm inside the Pujet model. I need to externalize it, but that's easy. Okay? And to make this become strict, is the Pujet model has to be strict in the first place, and this is why we use Pierre-Marie Pujet's. Okay, there are lots of other ways to strictify, which I won't detail here, or alternatives that we thought like maybe that's what we should use to be able to formalize stuff in this strict fashion. They all have some problems, or they haven't been worked out completely, and some of them are really nice. So in summary, this talk or this paper provides a technique for strictifying the substitution calculus of a model of type theory. So this works for intrinsic quotiented syntax, and we get something even stricter than usual extrinsic syntax, because all the functor laws and this kind of invariant style laws are also strict in this new model. And also we provide the first computer formalization of gluing style canonicity, which is a showcase of using this technique. We showcase using this technique. Okay, here's the ugly truth. Agda and cock hang when you try to compute with our new syntax, because it's like this Pierre-Marie style Pujet set. The Pujets, they are higher order, and the terms become really large. And yeah, so we weren't really able to do any computation with this, but in principle it should work. And we also lose some definitional computation rules for the eliminator of the syntax, but I don't think that this is a problem in practice. So the future work is that actually this method doesn't only work for type theory, it works for any language with bindings, okay, which is called a SOGAT. We want to implement a reusable library in which you have some combinators and you can apply this technique to your favorite language. And maybe we need direct efficient proof assistant support because these higher order Pujets are too slow. Thank you.
Thank you, Ambrus. I invite any questions. Anyone with questions, please move to a microphone. You forfeited the right to a second question. You only get one.
Hi, Max New, University of Michigan. I didn't understand what you meant early on. You said that in the when you work with the intrinsically quotiented, when you work with the initial model, that you're forced to use explicit substitutions. I mean, you could also just prove that that a syntax with defined substitution is also initial, right? So I don't understand what you meant by that. On your early slide.
Okay, yeah. So if you just work with the universal property of the initial model, then the substitutions will be just, substitution will be just a constructor. That's what I meant.
Okay, I see what you mean.
Yeah.
Okay. And then the other thing was I've implemented category solver based on this Yoneda lemma kind of approach, but when I did it, it was not actually definitionally associative because the proofs of naturality don't actually line up. So is there a way to make it work so that the proofs line up, or do you need definitional proof irrelevance?
Yeah, so yeah, the easy way is definitional proof irrelevance, but I can show you how to do it. It's very nice to make it work, even so that the proofs are also proof. You work with proof level proofs. What you need to do is to not say natural transformations, but you need to say parametric transformations. Okay. And then it's definitionally natural. Yeah.
Great. Thank you.
Please join me. Please join me. Am I working? Okay. Please join me in thanking Ambrus once more.